Good morning, everyone. Today we're going to explore something that might seem a bit paradoxical at first. What happens when functions grow without bound? Let me start with a question that might puzzle you. Can you talk meaningfully about limits when the function values become infinitely large? The surprising answer is yes, but we need to be careful about what we mean. Think about this. If I asked you what happens to 10 over x as x gets closer and closer to zero, what would you say? If you're thinking it gets huge, you're absolutely right. Today, we're going to make that intuition mathematically precise. So let's start by looking at a concrete example to build our intuition. Consider the function f of x equals to 3 over x minus 2 squared. I want you to imagine what happens as x approaches 2. Let's calculate some values together. So let's see what happens when we start approaching from the right side to 2 and from the left side to our 2. So if we take a point that is close to 2, let's say 2.1, we have 3 over 2.1 minus 2 squared. That's going to be 300. What if we start approaching from the left side? We'll take a value of 1.9 and we have 3 over 1.9 minus 2 squared. That's going to be also 300. So it seems that we are approaching some value, 300 in this case. So maybe we're approaching actually 300 here. Let's check. So let's grab another value that is closer to 2, but is a bit away from 2.1. So let's say 2.01 would be a good value to check. So we have 3 over 2.01 minus 2 squared. And in this case, we have 30,000. Now let's check what happens on the left side. We grab 1. Let's say 99, right? It's closer to 2. So we have 3 over 1.99 minus 2 squared. That's going to be 30,000. Okay, so now it's not 300, but 30,000. And maybe we're approaching something close to 30,000. Let's check a closer value, right? So let's check 1.999, 3 over 1.999 minus 2 squared. In this case, we have 3 million. And on the right side, if we choose 2.001, we get 3 over 2.001 minus 2 all squared. We have 3 million here as well. Okay, so we see that when we approach 2 from the left side, the values are increasing in magnitude. And if we approach 2 from the right side, the values are increasing in magnitude as well, from 300 to 30,000 to 3 million. And if we move even closer, let's say we choose a value that is something like this, 2.0001, it will be even a bigger number in the magnitude with a positive sign. So we can say that we're approaching from the left or from the right enormously large value. So as you can see, they're not approaching any finite number. This is what we call infinite limits. So we're both approaching, from both sides, we're approaching positive infinity. Now let me give you a formal definition. Don't worry if it seems abstract at first, we'll work through plenty of examples. We write limit of f of x as x approaches a equals to infinity if f of x grows arbitrarily large for all x sufficiently close but not equal to a. Similarly, we write limit of f of x as x approaches a equals to negative infinity if f of x is negative and grows arbitrarily large in magnitude for all x sufficiently close to a. So important note here is when we write limit of f of x equals to infinity as x approaches a, this one or this one, we're using special notation. The limit doesn't actually exist in a traditional sense. We're describing a specific type of unbounded behavior. Now let's go back and analyze again the example that we did. Limit of 3 over x minus 2 squared as x goes to 2. So this is the function we've looked at, and let me explain what's actually happening. So the numerator is a constant 3, and denominator is x minus 2 squared. So squared means that it's always positive. As x approaches 2, the denominator approaches 0. So what we have here is positive constant over positive number that is approaching 0. So we would have here a positive infinity. Therefore, the limit would be equal to infinity. Now here's where things get interesting. Consider limit of 2x minus 8 over x minus 4 as x approaches 4. Let's think about this carefully. When we plug in 4 directly into the function, we have 2 times 4 minus 8 over 4 minus 4. We get this form 0 over 0, indeterminate form. Now let me factor the numerator. Limit as x approaches 4 of 2x minus 4 over x minus 4. And as you can see, we can cancel x minus 4, and we have limit as x approaches 4 of 2, that's going to be equal to 2. This shows that not every fraction with the 0 denominator gives an infinite limit. The key is whether the numerator is also approaching 0. So let me look at another example. Limit of x plus 3 over x plus 1 cubed as x approaches -1. This time the denominator is cubed, not squared, which changes everything. So for this limit, we will be looking at left and right side. Limit of my function as x approaches -1 from the left side, and limit of my function as x approaches -1 from the right side. Now, what does it mean to approach from the left side? We will be plugging in value into our x that is close to -1, but from the left side. What are these values? So remember, we have -1 right here. So all the values on this side are going to be -1.1, -1.01, and so on and so forth. From this side, those will be -0.9, -0.99, and so on and so forth. So from the left side, we're picking a value that is close to 1. We would have -1.01 plus 3 over -1.01 plus 1 cubed. So as you can see, in the numerator, we have approximately 2, and in denominator, we have approximately 0, but it's going to be negative value, actually -0.000, I don't know, many zeros, 1, right? So when we have in the denominator a very small number and negative, in numerator just regular, I don't know, something like 2 and positive, then we will have the whole fraction would be negative infinity in this case. On the other hand, when we have on the right side, we're picking a value that is close to 1. So we have -0.99 plus 3 over -0.99 plus 1 cubed. So numerator doesn't change. It will approximately have 2, right? And the denominator, that's going to be also 0.01, but with the positive sign now because 1 is greater, right? So we have 0.01, and that's cubed. So we have a very small value in the denominator. So the whole fraction will be positive infinity. Since we get different results for each side, we say that two-sided limit doesn't exist, not even at infinity or negative infinity, right? So these are not coinciding. So we have limit as x approaches -1 of x plus 3 over x plus 1 cubed does not exist. Now that we understand infinite limits, let's connect them to a graphical concept you've seen before, which is vertical asymptotes. So the line x equals to a is a vertical asymptote of f if at least one of the following is true. Limit of f of x is equal to positive or negative infinity as x approaches a, or if we have limit from the right side or from the left side equals to positive or negative infinity. In other words, a vertical asymptote occurs whenever the function has an infinite limit. Consider f of x equals to x squared minus 4 over x squared minus x minus 6. First, let's factor completely. We have x minus 2, x plus 2 over x minus 3, x plus 2. So now we need to identify where the denominator equals to 0. The denominator equals to 0 at x equals to 3 and x equals to -2. Now we check both of these points. At x equals to -2, limit as x approaches -2 of x squared minus 4 over x squared minus x minus 6. When we do the direct substitution, we get -2 squared minus 4 over -2 squared minus -2 minus 6. We have 4 minus 4, that's 0, and we have 0, so we have indeterminate form. What does it mean? That means that we need to manipulate this expression to find the limit. So that means that the limit actually exists, but we need to first simplify this expression to find that. So as before, let me write this expression factored out. I have limit as x approaches -2, x minus 2, x plus 2 over x minus 3, x plus 2. And I can cancel this x plus 2 here, and I get limit as x approaches -2 of x minus 2 over x minus 3. Now I can try to plug in -2 directly. I have -2 minus 2 over -2 minus 3. That is going to be -4 over -5, which is 4 over 5. So this is our limit. The limit exists in this case. Now let's check another point, x equals to 3. Limit as x approaches 3 of x squared minus 4 over x squared minus x minus 6. When we try to directly substitute 3 into the expression, we have 3 squared minus 4 over 3 squared minus 3 minus 6. We have 9 minus 4 over 9 minus 3 and minus 6. That is going to be 5 over 0, right? So if this is the case, when you have a number that is divided by 0, this is where we have the vertical asymptote. So in this case, what we need to do is we need to look at the left side of 3 and right side of 3. From the left side, let me write this as factored out. So I have x minus 2, x plus 2, x minus 3, and x plus 2. I can actually cancel these two, and I have limit as x approaches 3 from the left side, x minus 2, x minus 3. So now when I'm plugging in the value that is close to 3 from the left side, it's something like 2.99 minus 2 over 2.99 minus 3. The top portion is going to be close to 1. At the bottom portion would be something close to 0 with a negative sign, right? So in this case, we are approaching a negative infinity. On the right side, limit as x approaches 3 from the right side, I will just write this simplified version of that. So x minus 2 over x minus 3. I will plug in the value into my x a bit bigger than 3. So something like 3.01 minus 2 over 3.01 minus 3. As you can see on the top, we have something close to 1 and a value that is close to 1. And in denominator, I have a value that is approaching 0, but from the positive side. So I have here a positive infinity. So x equals 3 is a vertical asymptote. So the key insight, vertical asymptotes occur when the denominator is 0, but the numerator is not 0 after all the cancellations. And in determinant form, when we have 0 over 0. In this case, we still need to manipulate a function, and we can find the limit. It's not infinity. Now let's explore infinite limits with some trigonometric functions. These can be tricky because functions oscillate sometimes. So let's consider a function tangent of x. So let's find limit of tangent of x as x approaches pi over 2. Remember that tangent is sine x over cosine x, right? So what happens at x equals to pi over 2? Remember that sine at pi over 2 is equal to 1, but cosine at pi over 2 equals to 0. So you have this exactly scenario where we have 1 over 0. In this case, this is not in determinant form. That means that you don't need to manipulate a function to find the limit. That means that you don't actually have a limit as a single value. You have an infinite limit here. So from the left, as x approaches pi over 2 from the left side, sine of that pi over 2 from the left side is going to approach 1, still positive value. And cosine of pi over 2 from the left side is going to approach 0, but with the plus, right? It's going to still be positive. So it's we can also say that it's greater than 0, but very close to 0. It's slightly less than pi over 2 for a value that is slightly less than pi over 2. Therefore, limit of tangent x as x approaches pi over 2 would be positive infinity. Now from the left side, that's that for the left side. Now for the right side, when x approaches pi over 2 from the right side, my sine of pi over 2 with positive sign is still gonna approach 1 because it's the second quadrant, right? So that's gonna be right here, pi over 2. So for this case, we were approaching pi over 2 from the first quadrant. For the second case, we're approaching from the second quadrant. And remember that sine is positive here, and also sine is positive here. Cosine is positive in the first quadrant, but it is negative in the second quadrant. So my cosine of pi over 2 from when we approach from the positive side is going to be 0, approaching 0, but with the negative sign. So that means that limit of tangent x as x approaches pi over 2 from the right side is going to be negative infinity. And we say that limit of tangent x as x approaches pi over 2 does not exist because one is positive infinity, another one is negative infinity. So x equals to pi over 2 is a vertical asymptote of tangent x. And in fact, x equals to pi over 2 plus n pi for any integer n are all vertical asymptotes. Now let's try another example. limit of secant x as x approaches 0. Recall that secant x is 1 over cosine. And at x equals to 0, we have 1 over cosine 0, which is 1 over 1, which is going to be 1. So limit as x approaches 0 of secant x is actually going to be 1. No infinite limits here. The function is actually continuous at x equals to 0. But what about as x approaches pi over 2? Limit of secant x as x approaches pi over 2. Cosine of pi over 2 here is 0, so we have the scenario of 1 over 0. In this case, remember that we have a vertical asymptote in this case, and one of the limits is negative or positive infinity, and we might have 3 scenarios here. Whether the limit does not exist, if one goes to positive infinity and another goes to negative infinity, or if they both are positive infinity, then we have positive infinity. If both sides, left and right, are negative infinity, then we have negative infinity. So for this scenario where we have something over 0, these are the 3 options that we have for our limit. So let's check what we have in this case. So from the left side, as x approaches pi over 2 from the left, we have cosine x approaches 0 with the positive sign. So the secant x is going to be approaching infinity. From the right side, cosine is going to be 0, but with the negative sign, because that's the second quadrant. So secant x will be approaching negative infinity. So in this case, we say that limit as x approaches pi over 2 from both sides of secant x does not exist. So before we wrap up, let me highlight some common mistakes to avoid. First one, we assume that every 0 in denominator creates an infinite limit. Remember that you need to check if the numerator is also 0. If you have 0 over 0, this is what we call a removable discontinuity. In this case, you still have a limit. You just need to work with the function, simplify it a little bit, maybe multiply by the conjugate to find that limit. If you have a value over 0, let's say some n over 0, in this case, you might have your limit as infinity or it doesn't exist. And remember that when we write limit equals to infinity, it doesn't mean that the limit actually exists. This is the special notation, and the limit, it doesn't exist in a traditional sense. Okay, now another mistake is forgetting to check both sides of the limit. So the behavior might be different from each side. So you need always to check that when you're dealing with the limits with infinity. And another thing, you need to remember that vertical asymptotes occur when we have infinite limits.